Okay, so we've talked about depth perception, and now we'll talk about motion perception. These are learning objectives. All right, so let's play with our eyeballs a little bit. So just take your finger to the corner of your eye and just gently kind of move your eye up and down, and you should see the world kind of move around, all right? And it won't be very clear if you do that, okay? But moving our eye creates kind of the perception of movement. Right? If you stare at a waterfall for an extended period of time, all right, the water's coming down, and then you look at, say, the rock wall next to it, it'll appear that the wall is moving up. All right? We have special the receptors in our have special ganglion cells that are sensitive to motion, right? And they're sensitive to particular directions of movement. So you have ones that are kind of sensitive to downward movement, and if you do that long enough, they fatigue, and their opponent process is upward movement. So they fatigue in this way, and it strengthens the upward movement of things. Okay? But we just have a ganglion cell that's sensitive to movement and the direction of movement. Movement is extremely important for survival. Okay? We live in a world where things move around, we move around in it, and we have to be able to distinguish our movement from the movement of things, okay? And we have to be able to distinguish the movement of our eyes from the movement of things, okay? But the value in that is that we need to know if something that's moving is moving towards us in some threatening manner. We need to be able to judge the speed and direction of what's moving. Okay? This morning I was walking my dog and my youngest daughter's dog. She's visiting, and we were walking through the woods, and I saw, well, they saw the movement first, and I didn't. At first I thought maybe it was a deer, and I realized it was too big for a deer, and I thought maybe it was a fox. Well, it's too small for a deer, excuse me. And then I realized it was too big for a fox, and realized it was a coyote. Okay? But the coyote was moving away and was really more scared of us than we were. Okay? But that's the importance of being able to access movement. You have to be able to judge what's out there in the world. Okay? Now, there are people who are blind to motion. Okay? So they can see objects, but as soon as the objects start moving, they lose it. All right? And you can think about how hard it would be to pour a glass of water when you can't see the water move into the cup, or crossing a street, watching a sporting event, or even trying to sit through a lecture if the professor is moving around and doing anything. Okay? This is really maybe the oldest form of visual perception, is movement perception. And it's the edge of our retina is really only detecting movement. And again, we don't have a lot of visual acuity there, but it's important to be able to be aware of anything that could be possibly moving to the side of us. Okay? And motion helps us with object perception. Okay? All right, so let's talk a little bit about the importance of it. I was blowing leaves in my driveway one fall, and the leaves had a certain pattern of movement. As the blower hit it, they would kind of move up and float a little bit. But just out of the corner of my eye, I noticed something that was moving in a very different pattern from that. So I stopped blowing and took a look and realized it was a baby copperhead. Okay? You can always tell a baby copperhead by the green tail that's there. You can see the pattern, copperhead kind of pattern. But this is how help you distinguish behind other baby snakes that might have similar patterns. It's that green tail. Right? So I took care of the little baby copperhead. I hated to do it, but I didn't really want copperhead growing up and biting my dog or anyone who's here to visit. So at this point, the copperhead's not alive. But it was a little spooky to all of a sudden realize, there's a copperhead in the leaves. Just as there's obstacles to every type of visual perception we've talked about, there's same with motion perception. The big thing is we have to differentiate between our eyes, which are constantly moving, versus the object moving. Okay? If we're walking through the world, moving through the world in any manner, we have to distinguish our movement from the movement of things around us. Right? In fact, as we move through the world, it looks like things are moving. Right? They move we're moving, but it gives the sense of motion to other things as well. Okay? So we need to identify movement when a moving object's not moving across the retina. Okay? And we need to be able to integrate both the what and where streams, because we have to be able to identify the object we're looking at. We have to identify where it is from us, and in addition to just the movement of it. Okay, so if we keep our eyes still, okay, eyes don't move. If something is moving across the world, it will move across our retina, which means it will stimulate one photoreceptor, then the next, and then the next, then the next, okay? And that's the easiest way to detect motion, okay? Our eyes still and something's just moving across our retina, sequentially stimulating each of our photoreceptors and the other neurons in our retina. There's a problem with this because our fovea is such a small area. We have such a small area of acuity that what it does is it creates a lot of ambiguous motion. And you can experiment with this a little bit. Just create an OK sign, all right, and then put a pencil or your finger, and don't let yourself see the ends of that. But you can see that, say it's a slight diagonal movement up versus straight across can be really hard to differentiate. And the smaller you make that OK sign, the harder it is to actually determine the movement. Okay, so this is a way, but it doesn't clarify all the time what ways things are moving. An example of that is this the barbershop illusion. Okay. This is just spinning around in a circle. Okay. But you have the illusion of stripes, of something that's actually spinning up. Okay? Well, what about tracking a moving object? Okay? So let's say, like I talked about the coyote this morning. Okay? So I could track the coyote as he moved through the woods. Okay. And I can track that coyote by keeping my eyes fixated on the coyote, and so as the coyote moves, my eyes move. All right? And in this case, now we have the object's kept stable on the retina, so it's not moving across the retina, but my eyes are moving. Okay? So we've talked about two things, right? Something could move across our retina when the retina is not moving, or our retina could not move while an object the objects, because we're tracking the object on our retina, the object is stable, but the retina is moving. Okay? So we have to distinguish between those two. And one way to explain that is what's called corollary discharge theory. Okay? There's this hypothetical, at this point, part of the brain called the comparator. Okay? This is just a model. There's no part of the brain that's actually been identified as the comparator. But the idea is that there's some part of the brain where information about eye movement feeds into, and information about sensation on our eye moves into it. Okay? So what's coming into our retina is fed up to here, and what's being the signals to our eye about whether to move or not move are coming in here. Okay? And now it can compare is there something coming in, and are our eyes moving? And based on that, it can determine whether or not there's actual movement. Now, the big question here is where could that be? Yeah? And there's no, as I said, no specific area that's been identified, but there's plenty of places, plenty of interactions between our what and where pathway where that could happen. This, by the way, is the area that's important for detecting movement. Okay, so one thing that's important to note is that we talked about perception as detection of information, making sense of it, and acting. And I made the point that all of this is happening at once. Right? But when we talk about movement perception, it really becomes clear of how movement and sensation are tied together. You can't have one without the other. Okay? In this case, we have to distinguish between movement of the object and movement of our eye. So let's talk about our eye movements, the little tiny movements. They're called saccades. Our eyes are darting back and forth about 3 to 4 times per moment. Okay, just when when we're not really focused on something, and then when we're trying to focus on something and get detail, we'll have little bigger size saccades. Okay, and every time our eye moves, then things should be blurry, just as when you took finger to the corner of your eyeball and just gently moved it up and down. Okay? That's how the world should look all the time, because our eyes are constantly going back and forth. Well, it's our superior colliculus that is responsible for our eye movements. Okay? And that's arranged, our retina is mapped out in the superior colliculus, and it has 6 layers of columns, just like our lateral geniculate and our cortex. So it's arranged in a very similar way. And one layer has the input from one eye, other layer the input from the other eye. One of the things it does, without going into a lot of detail of it, is that our what the superior colliculus does is it creates a pattern of neural activity based on what it's currently looking at, and it anticipates what will be when the eye moves to the next spot. Okay? If I'm expecting something to be, say, here, right? And then when my eye gets to there, it's not there. That's another way that I can detect, I can be aware of movement, right? Because if it's stationary, it should be there, but if it's moving when my eye gets there, it should be in a different spot. Okay? But the other thing that's happening here in terms of all those little saccades is that the sensory input from the eye actually turns off between each movement. Okay? So as the eye moves, there's no sensory input. Okay? And what we're seeing, because the world doesn't go blank on that, is called the transsaccadic memory. Trans meaning across the saccade memory. Okay? And so each time our eye moves, what we're seeing is a memory of what we just looked rather than the actual image of what's there. Okay? And you can test this out. Look in a mirror, okay? And when you do, you won't see your little tiny eye movements. But you look at someone else's eyes, you will. You can't see yours because what you're looking at is the memory of where your eyes were, not. But when you're looking at someone else's, your visual input isn't shut off because their eyes are moving, right? And this is the way that our perceptual system maintains a stable image over time. Same thing with eye blinks. Your eyes blink constantly, and every time your eyelids close, all right, the world should go dark, and yet it doesn't. Okay, so that would be the trans eye blink memory. All right. Apparent motion is when things look like they're moving and they're not. Okay. If you ever see a kind of a neon sign where it looks like the words are moving, or it has an arrow that seems to be flashing forward, all right, go this way, and so the lights are kind of going do, and it looks like it's moving. It's not. It's just that you just have the lights moving in sequence to create this movement. Okay. Talked about stroboscopes and we talked about the Gestalt balls of perception. Yeah, that creates apparent motion. And sometimes it looks like Mars is moving backwards in the sky. It's not. It's just because of where it is and things that are more in front of it, it'll give the appearance of moving in a different direction. All right, see if we can get this going. Oh.